Hello, I'm Daniel Mayerson. Thank you for listening to my talk. I'd like to tell you a little bit about my recent work with Iosif Bena, who is, as me, at the IPHT at the CEA Saclay in France. And I'd like to tell you a little bit about my recent work about multipoles and multiple ratios of black holes. And I hope to convince you in these few minutes that these multiple ratios are really new properties, at least the way that we define them, the way that we compute them, are really new properties of black holes, including the simple Kerr black hole that until now have not really been understood or known. For more information, you can always look at these two papers here on which this talk is based. So without further ado, let's get going. I'd like to tell you a little bit about gravitational multipoles just to set the scene. And then I'm going to tell you about introducing these multiple ratios, these new quantities for the Kerr black hole, the simple Kerr black hole. I'll also tell you a little bit about how to calculate these for the multiple ratios for the supersymmetric black hole, which is of more theoretical significance than the Kerr black hole, of course, which also has observational consequences, which I will then talk about in the last part here. So just to set the scene, multipoles, or of course the multipole expansion, is of course something that we all know from, for example, electrodynamics, and essentially it's just a 1 over r expansion where each term comes with a more and more subleading power of r. And so we start usually with the monopole, then we go to a dipole, quadrupole, octupole, and so on. Now doing a 1 over r expansion in GR might seem problematic because we have coordinate transformations or general coordinate invariants. And so you might wonder or worry that these multipoles are not well defined. That's of course a valid worry, but the solution to this was given in the 60s and 70s by Gerrard and Hansen and the Thorne formalism. And so these formalisms assure us that we can indeed define two families of gravitational multipoles. These two families are the mass multipoles, which are generally denoted by ML, and the current multipoles, which are generally denoted by SL. The mass multipoles are essentially a 1 over r expansion in some coordinates of the TT component of the metric, and the T phi component of the metric has a 1 over r expansion that gives you the current multipoles. The multipoles that we know the best are, of course, the mass, which is just m0, and the angular momentum, which is just s1. The most basic example is the Kerr black hole, so just rotating uncharged, which has two parameters, m and a, and so the multipoles there are the even multipoles, the even mass multipoles, and the odd current multipoles are non-zero, but importantly also the odd mass multipoles and even current multipoles are zero, they vanish. So this leads us to our next topic, which is which are multipole ratios of Kerr. Now, as I just said, there are a bunch of multipoles that vanish for Kerr, and so you can consider some multipole ratios that are actually ill-defined in a naive sense. So, for example, I've considered this multipole ratio here, where both the numerator and denominator contain a multipole which is 0. So S2 and M3 are both 0 for the Kerr black hole. And so this is a 0 over 0 ratio. It's not really well defined. This ratio is undefined for the Kerr black hole. However, and this is our main method, our main result, if you embed this Kerr black hole into a general string theory, and you deform the Kerr black hole to a more generic, more general string theory black hole, and in particular, although I won't give more details, we're thinking of the most general STU black hole with 10 parameters, which is given in a paper by Kerr and Chow. If we deform the Kerr black hole into this more general black hole, and then take away the deformation again, we take the limit where the deformation goes to 0, then actually this ratio becomes a well-defined quantity. So this quantity here in the square, or in the rectangle, is sort of our main result, where we simply say that we take the limit where the deformation of the black hole goes away and we retrieve the Kerr black hole again. And in this limit, we can associate this multipole ratio, this well-defined multipole ratio, to the Kerr black hole. So, this is not a crazy procedure. An analogy for this is simply as a very simple thing. For example, sine 0 over 0 is, of course, an ill-defined quantity, but as a limit of sine x over x, it's simply 1, right? And this is exactly the same kind of procedure that we're doing here, basically. A few examples. So the ratio that I considered above, over here, so where we had the S2 over M3 problem, because these are below 0. If you do the procedure that I just talked about here, then you simply get 1 for this ratio. A more complicated ratio or family of ratios is this guy here, which is a different ratio for each value of L. And so depending on L, you get a different number over here, but it's simply a simple function of L. And note that for each L, this quantity here is ill-defined for Kerr because it's always going to be 0 over 0. So this gives us really a way of defining, of associating an infinite number of new properties, of new numbers to the Kerr black hole. Now, not only does this give us an infinite number of new properties, of new characteristics of the Kerr black hole, but it also gives you an immediate prediction for small deviations of Kerr. So if you imagine that you have some theory, some model where the Kerr black hole is replaced by a small perturbation of the Kerr, then this prediction that we have here is a prediction from string theory that constrains the perturbative small deviations from Kerr. So in particular, if we imagine that we perturb Kerr by some parameter epsilon, or some dimensionless small parameter, then the multipoles, or the changes of multipoles, have to be given by this one parameter family of small multipole deformations away from the Kerr multipoles. So this is a very strong constraint of models for deviations of Kerr, at least if you want them to fit with string theory. If you want them to be something that can mesh with string theory, then they have to fit, then their multipoles, the multipoles that they predict, have to fit within this one parameter family of multipoles. So just to talk about supersymmetric black holes also for a minute, the supersymmetric black hole in 4 dimensions is, of course, something that's less interesting for observations, but is nevertheless of great theoretical interest. So we could do the same procedure for this supersymmetric black hole. Now in 4 dimensions, supersymmetric black holes are necessarily non-rotating, and so all of their multipoles vanish except for the mass. Now we can do exactly the same thing where we deform this black hole into a more general black hole and then take the limit where we take away the deformation, and we can again associate these the resulting limit of these ratios to the supersymmetric black hole. Now that's one way that we can actually calculate it. Now for the supersymmetric black hole, we have a different way that we can also calculate these ratios. For supersymmetric black hole, there are things called fuzzballs, or microstate geometries, where in essence we take the black hole and its event horizon and we replace the black hole, the event horizon, by some smooth geometry on the inside of the throat, let's say, of the black hole, some smooth cap. And so we call these bubble geometries because these in extra dimensions. When you introduce the extra dimensions to string theory, you can think of these as bubbles. And so these are supersymmetric, smooth, so there's no singularities. They have no horizon, and they have the same asymptotic charges as the black hole. So they look like the black hole from far away, and it's only when you're very, very close to what you thought was the horizon that you see this extra structure. And so the second way that we can calculate a multipole ratio is simply by taking the multipole ratio of this microstate geometry, the resulting and associating the resulting number to the supersymmetric black hole as well. In that context, I'd like to also mention very briefly these 2 papers by these authors who also talk about multipole ratio or multipoles of microstate geometries, of fuzzballs. Now these 2 ways, just to distinguish them, I'll call this the indirect way because it involves taking the original black hole and deforming it away from the original black hole and then going back to the original black hole. And this the direct way because we're really taking a microstate of the original black hole. So these two different methods, you can compare them, of course, for certain black holes. And so without going into a lot of details, this is a comparison of certain multipole ratios for certain multiple orders for 2 black holes. And so you see that a general feature is that at low multipole orders, these 2 methods agree very well, the indirect and direct ways. And it's only when you go to higher multipole orders that these 2 start disagreeing somewhat. So this gives us sort of an extra piece of evidence that our methods of introducing these multipole ratios or these limits of multipole ratios as fundamental properties of the black hole is really something that seems to make sense. Okay, so finally what I'd like to do is first let me summarize the most important point of our method. For Kerr, of course, because that's what we all care about when we look at black holes in the sky, we were able to define new multipole ratios, to really associate these new multipole ratios as properties of the Kerr black hole by deforming it away to some generic black hole in string theory and then taking the deformation to 0. And as I try to convince you, this gives you a string theory prediction for small deviations away from Kerr. Now, a little more speculative, we can think about what the observational consequences of this might be. And so one thing is you might think that the late time relaxation after a black hole forms is governed by these multipole ratios. So in particular, you might think that a black hole may form and then there's going to be some multipole radiation until it asymptotes to the Kerr stationary black hole. And the way that these multipole radiation dies out at late times is then have to be related to each other. So the different multipoles can't die out independent from each other. They have to be related by these multipole ratios that we've computed. And so you might think this sounds a lot like the properties or theory of quasi-normal modes, and so it's very interesting to think of what might be the relation of our multipole ratios to quasi-normal modes of the black hole. And so that's an interesting open question. Now, a final thing that I want to point out is, if you go out to nature and you measure a black hole and you measure multipoles or multipole ratios, and let's say they agree with our predictions, then of course that's great, and that means that what we did makes a lot of sense, and so what we are measuring out there is the Kerr black hole or a small deformation of the Kerr black hole. That meshes with string theory. But however, if you would measure these multipoles or multipole ratios of a black hole in nature, and it doesn't agree with our prediction, then there's two possibilities. One possibility is, of course, that this black hole that you've measured, these deformations that you see, are in a theory that is not string theory. So, of course, that's a possibility. But a much more exciting possibility is that this is a smoking gun signal that really what we're seeing in the sky is not anything like a black hole. It's not really just a small deformation of a black hole. It's really something that's telling us that the horizon scale physics has to be very, very different than the black hole itself. So instead of having a black hole or even a small deformation of the GR black hole, like the Kerr black hole, we really need to replace the entire black hole by something completely different at the horizon scale already. And so that's something like a fuzzball in string theory. Okay, so that's all I wanted to say. Thank you very much for listening to my talk.